A unique value of H3D's technology is our omnidirectional gamma ray imaging capabilities. But how do we do it? In the next few minutes, we'll break down how it works so you can better understand how to apply this technology to your applications. When a gamma ray interacts in H3D's 3D position-sensitive CZT, one of the three types of gamma ray interactions will occur. These are photoelectric absorption, Compton scattering, or pair production. In all three instances, an electron cloud is produced whose charge is proportional to the energy the gamma ray deposited during the interaction. The electron cloud will drift to the anode surface due to the application of voltage to the detector, and a signal will be collected on one of our anode pixels. Which pixel collects the charge provides us the X and Y position of the interaction, and the depth of the interaction can be known from the drift time. For every interaction in the CZT, we therefore know the 3D position and energy. If a gamma ray undergoes Compton scattering followed by photoelectric absorption inside our detector, we would know the position and energy information for each interaction, which enables us to perform Compton imaging. Compton imaging is a technique that uses the Compton scattering formula to determine the angle of scatter between the incident and scattered photon. The angle of scatter implies a cone of potential source locations that can be represented as a ring on the surface of a globe surrounding the detector. As more photons enter the detector and interact, more rings are overlaid. With few rings, you cannot know the source location. But as you get hundreds and eventually thousands of rings, they will overlap and converge on the location of the source. We can then unfold the globe like a map of the world and overlay the gamma ray image on an optical image. But what if the gamma ray didn't undergo Compton scattering? Coated aperture imaging is a technique that images gamma rays of energies that can be missed with Compton imaging. Coated aperture imaging visualizes gamma rays that interact with the CZT crystal only one time via photoelectric absorption. Inside compatible H3D systems, thin pieces of tungsten form a patterned mask that sits between the source and detector, blocking low-energy gamma rays. When gamma rays interact with the CZT, potential gamma ray source locations are projected back through the gaps in the mask. Similar to Compton imaging, as more gamma rays interact, the potential locations of the source will eventually converge. This coated aperture gamma ray image can be overlaid on an optical image to show the location of the source in the real world. By using a combination of Compton imaging and coated aperture imaging with an optical camera, H3D technology creates high-quality radiation images that accurately show where the radiation is located. And on the right is a coated aperture image of the same source. H3D uses these techniques to image radiation in nuclear power plants, for emergency ordnance disposal, CBRN emergency scenarios, and many other applications. If you'd like to know more, check out our website or contact us.